Welcome to this coding walkthrough. Today, we'll dive into the problem titled String Matching in an Array. In this problem, we'll explore how to identify strings in an array that are substrings of other strings in the same set. Let's get started. In this problem, you are given an array of strings called words. The task is to identify and return all strings in this array that are substrings of another string within the same array. A substring is defined as a contiguous block of characters that appears within another string. For instance, the string ABC is a substring of a BAP because ABC appears as a continuous sequence in a BAP. However, AC is not a substring of a BAP because the characters A and C are not contiguous. The output should be a list of all such substrings from the input array, and you can return the list in any order. It's important to ensure that the output does not contain duplicate values. The input will only include strings made up of lowercase English letters, and the task is to determine which strings meet this criterion. For example, consider the input array words equals mass as hero, superhero. Here, the string is a substring of mass because as appears as a continuous block within mass. Similarly, hero is a substring of superhero. On the other hand, mass and superhero are not substrings of any other strings in the array. Therefore, the output for this example is as hero. This demonstrates how the solution should identify only the strings that are substrings of another word while excluding others. Now, let's look at another example with words equals LeetCode in code. Here, ET is a substring of LeetCode because it appears as a contiguous block within LeetCode. Similarly, code is also a substring of LeetCode. However, the string LeetCode itself is not a substring of any other word in the array. Based on this, the output is ET code. This example further highlights how the solution filters and includes only the valid substrings from the input array. In a different case, consider the input words equals blue, green, BU. Here, no string in the array is a substring of another string. For instance, while BU appears as a part of blue, it is not a contiguous block. Similarly, blue and green are standalone and not substrings of any other strings in the array. As a result, the output for this input is an empty list, indicating that no substrings were found. Finally, let's discuss some constraints and edge cases. The length of the array words will be between 1 and 100, and each string in the array will have a length of 1 to 30 characters. All strings in the array are guaranteed to be unique. For edge cases, consider when no substrings exist, like words equals ABC, def, ghi, which results in an empty list. Alternatively, if all strings are substrings, such as words equals a hub ABC, the output would include all but the longest string, resulting in a hub. Lastly, if strings overlap but are not true substrings, like words equals hub, ba, ABC, the output should still exclude them, resulting in. These considerations help ensure the solution is complete and robust. To solve this problem, we need to identify all strings in the input array that exist as substrings within other strings in the same array. A substring is simply a contiguous sequence of characters within another string. Our goal is to return a list of these strings, ensuring there are no duplicates. One intuitive way to approach this is through a brute force method. Here, we compare each string with every other string in the array. For each pair of strings, we check if one string is a substring of the other using the AND operator in Python or equivalent functionality in other languages. The steps are straightforward. We loop through all strings using two nested loops, perform the substring check, and add matching strings to the result list. While this method is simple to implement, it has a downside. The time complexity is n squared asterisk k, where n is the number of strings and k is their average length. This is because each substring check can take k time, and we perform this for every pair of strings. The space complexity is n, as we only need to store the results. While this approach is easy to implement, it can become inefficient for larger inputs due to the nested loops and repeated comparisons. To improve upon the brute force method, we can use an optimized approach that involves sorting the strings by length before performing the substring checks. By sorting, we ensure that shorter strings are checked first, reducing unnecessary comparisons with strings of the same or smaller length. In this approach, we iterate through the sorted list. For each string, we only check if it is a substring of any longer strings that appear later in the sorted order. This reduces redundancy, as we avoid comparing against strings that are too short to contain the current string. The steps involve sorting the array, performing the substring check for each string against longer ones, and storing matches in the result list. While the worst-case time complexity remains O, n squared asterisk k, the sorting step, which is O, n log n, helps reduce redundant comparisons in practice. The space complexity is still O, n, for the result list. This approach strikes a balance between simplicity and efficiency, though it may still struggle with very large datasets. Another alternative is to use a tree data structure, which allows for efficient substring checks during insertion or traversal. In this approach, we start by inserting all strings from the array into the tree. The tree organizes strings in a way that makes it easy to check if one string is part of another. For each string, we traverse the tree to determine if it exists as a substring of any other string stored in the tree. If the condition is met, we add the string to the result list. This method has a time complexity of O, n asterisk k, where n is the number of strings and k is their average length. The space complexity is O, n asterisk k, as the tree has to store all strings. While this approach is more efficient than brute force for large inputs, it comes with the added overhead of building and traversing the tree. This makes it harder to implement and less practical unless the constraints are very large. For this problem, the brute force approach is the most suitable choice due to its simplicity and the manageable constraints of the problem. While the optimized sorting method and tree-based solutions offer performance improvements, their added complexity is unnecessary for the typical problem sizes encountered here. A few key observations make this clear. First, sorting strings by length simplifies the substring check by ensuring smaller strings are only compared against longer ones. Additionally, the if-and-in-b operation takes advantage of highly optimized substring search mechanisms built into modern programming languages. While a tree-based solution is powerful and efficient for large-scale problems, it is overkill for smaller datasets where the brute force method performs adequately. Ultimately, the brute force approach balances simplicity and performance, making it the preferred strategy for this problem. In this problem, we need to identify all the strings in the input array called words that appear as substrings within another string in the same array. Remember, a substring is simply a sequence of consecutive characters within another string. The goal is to return a list of these substrings without any duplicates. To solve this, we start by initializing a set called result. This set will temporarily hold all the strings that meet the substring condition, and because it's a set, it will automatically ensure that duplicates are avoided. Next, we iterate through each string in the words array using an outer loop. For every string we pick, let's call it word, we compare it against every other string in the array. This is achieved using a nested loop, where the outer loop selects the candidate word, and the inner loop iterates over the potential superstrings to check if word is a substring of any of them. Now, for each pair of strings, we proceed to check if the string word is indeed a substring of another string superstring. To avoid unnecessary operations, we ensure that we skip the comparison when word and superstring are the exact same string. Once we've filtered out identical strings, we use the in operator to check if word exists as a substring inside superstring. If the condition is true, we add word to the result set. After evaluating all pairs of strings, the result set will contain all unique substrings. However, since the problem requires the output to be a list, we convert the set into a list format as the final step. Finally, we return this list of substrings, which completes the algorithm. There are a few key insights to keep in mind about this approach. First, by skipping comparisons where word and superstring are identical, we avoid unnecessary checks and ensure that we are only identifying true substrings. Second, the use of a set for intermediate storage simplifies the process of removing duplicates. This avoids the need for any additional logic to ensure uniqueness. However, there is an efficiency trade-off with this brute force method. The nested loop combined with substring checks leads to a time complexity of O, n squared asterisk m, where n is the number of strings in the words array and m is the average length of the strings. This can become computationally expensive for large inputs. As for the data structures, we're working with three key components: the input array words as a list of strings, the intermediate set result for storing substrings, and the final output, which is a list converted from the set. This algorithm can be optimized to improve performance. For instance, sorting the words array by string length allows us to limit comparisons to cases where a shorter string is checked against longer ones. This reduces the number of unnecessary comparisons. Another possibility is using a tree, or prefix tree, to structure the strings in a way that enables faster substring searches. While effective, this approach does require additional memory. Additionally, advanced string matching algorithms like Rabenkarp or Knuth-Morris-Pratt (KMP) could be employed to speed up the substring checks. It's also important to account for edge cases. For example, if the input array is empty, we should return an empty list. If there's only one string in words, there are no other strings to compare against, so the output is also an empty list. Duplicate strings in the input are naturally handled by the set, which ensures that the output remains unique. Lastly, overlapping substrings, such as Anna and banana, should be correctly detected to ensure the solution is robust. This code solves the LeetCode problem 1408, string matching in an array, by identifying strings in the input list that are substrings of other strings in the same list. The function string matching takes a list of strings called words as input. First, a set called result is initialized to store unique substrings. A set is used to ensure no duplicates in the output. Next, the code uses two nested loops to compare all pairs of strings in the words list. The outer loop iterates through the indices of words using I, and the inner loop iterates through the indices using j. For each pair of indices, I, j, the code checks if words, j, is a substring of words, I, and ensures that I is not equal to j to avoid self-comparison. If the condition is satisfied, words, j, is added to the result set. After all pairs have been checked, the set result is converted to a list and returned as the output. This approach ensures that all valid substrings are identified without duplicates. The time complexity is O, n squared asterisk k, where n is the number of words in the list, and k is the average length of the words, as substring checks are performed for each pair of strings. The space complexity is O, u, where u is the number of unique substrings stored in the result set. This is the Java implementation of LeetCode problem number 1408, string matching in an array. The logic mirrors the Python implementation, iterating over all pairs of strings to check if one is a substring of another. Key differences include the use of Java-specific collections like hashset and ArrayList, as well as explicit type declarations for variables and return types. The method accepts an array of strings and returns a list of substrings found in other strings. To solve this problem, we start by initializing the result variable as an empty set. This will help us store unique substrings as we identify them. Next, we iterate over all pairs of words in the input array using two nested loops. The outer loop focuses on the current word, while the inner loop compares it to every other word in the array. For our first example, the input is mass as hero, superhero. When the outer loop selects the word mass at index 0, the inner loop begins checking it against the other words. We skip the case where the indices are the same, as a word cannot be a substring of itself. When as is compared to mass, we find that as is indeed a substring, so we add it to result. The next comparisons with hero and superhero yield no matches, so we move on to the next word in the array. Now, the outer loop selects the word as at index 1. Since as is shorter than mass, we skip checking whether mass is a substring of as. Similarly, we skip comparing as to itself. The remaining inner loop checks against hero and superhero, but neither contains as, so no new substrings are added. Next, the outer loop moves to hero at index 2. Here, we find that hero is a substring of superhero, so we add hero to result. Other comparisons for this word find no matches. Finally, the outer loop selects superhero at index 3. Since it is the longest word, no other word can be its substring, so no changes are made to result. At the end, we convert the result set to a list, which gives us, as, hero, as the final output for this example. In the second example, we have the input, LeetCoder, LeetCode, OD, ID, code. Again, we initialize result as an empty set and iterate over all pairs of words. The outer loop starts with LeetCoder at index 0. Here, we find multiple substrings. LeetCode is a substring of LeetCoder, so we add it to result. Similarly, OD, IT, and code are all substrings of LeetCoder, so we add each of them to result as well. The set now contains LeetCode, OD, IT, code. For the remaining outer loop iterations with shorter words like LeetCode, OD, ET, and code, no additional substrings are found because these words do not contain any of the others as substrings. Finally, we convert the result set to a list, which results in the output, LeetCode, OD, in code, for this example. In the third example, the input consists of the words A, B, C. After initializing result as an empty set, we iterate over all pairs of words. However, none of the words are substrings of each other, so the result set remains empty throughout the process. In the final step, we convert the empty set to a list, which results in an output of an empty list. This highlights that the algorithm correctly identifies when no substrings exist in the input array. To understand the time complexity of this solution, we need to break it down into its components. First, the outer loop iterates over all n words in the list, so it runs n times. Then, for each iteration of the outer loop, the inner loop also iterates over all n words, creating a nested loop structure that runs n*n, or n-2, times in total. Now, within this nested structure, we perform a substring check using the in operator to determine if one word is a substring of another. This operation depends on the lengths of the two words involved. If the word being searched has a length of m_i and the substring being checked has a length of m_j, the in check takes O, m_i*m_j, in the worst case. Finally, whenever a word is added to the result set, the operation takes constant time, O1, on average, due to the efficiency of hash-based insertion. These individual components lay the foundation for our complexity analysis. Now, when we consider the overall time complexity, let L represent the average length of the words in the list. The substring operation, which is the most expensive, contributes O, L squared, for each pair of words. Since there are O, n squared, pairs in the nested loop, the total time complexity becomes O, n squared * L squared. This remains consistent in both the best and worst cases because the substring check dominates the runtime, regardless of whether one word is actually a substring of another. Shifting focus to space complexity, the input list words requires O, n*L, space, since it stores n words each of average length L. Additionally, the result set, which collects the words that are substrings, could potentially store all n words in the worst case, requiring another O, n*L, space. Variables like I, j, and the result set reference itself only require constant space, O1. Together, the space complexity combines these factors. The overall space complexity is therefore dominated by the input list and result set, leading to a final space complexity of O, n*L. To put this into perspective, consider the naive approach, where we would generate all substrings of a word before checking them against the entire list. Generating substrings for a word of length L takes O, L squared, and comparing each substring with n words results in O, n*L cubed, for a single word. Repeating this for all n words gives a total time complexity of O, n²*L cubed. By contrast, our current approach avoids explicitly generating substrings and instead uses the in operator, which reduces the total complexity to O, n²*L squared. This is a significant improvement. Finally, the mathematical justification for this big O result lies in the substring check, which operates in O, L squared, and dominates the runtime. Since it occurs for each pair of words, the overall runtime scales as O, n²*L squared, with all other operations being negligible in comparison. When tackling this problem, there are several common mistakes to be aware of. First, if your input array contains duplicate strings, failing to account for this can lead to redundant entries in your result. To avoid this, consider using a set to store results or filter out duplicates before processing. Another frequent mistake is misinterpreting what defines a substring. Remember, a substring must be contiguous, so methods like the in operator in Python or index of in Java are ideal for proper checks. Additionally, a purely brute force approach, which compares each string against every other, can become inefficient for large inputs. While such a solution may work, its time complexity of O, n superscript 2*k, makes it unsuitable for larger datasets. Finally, edge cases like empty strings, single-element arrays, or strings being substrings of themselves are often overlooked. Always test your solution against these cases to ensure robustness and prevent runtime errors. Another important consideration is ensuring your results are free of duplicates. Without explicit deduplication, your solution might include repeated substrings in the output. Using a set or carefully managing your results list can help maintain uniqueness. Now, from an interview perspective, the essence of this problem lies in efficiently checking if a string is a substring of others in the array. Sorting strings by length can minimize unnecessary comparisons, as shorter strings cannot contain longer ones. For more advanced optimization, hash-based lookups or data structures like suffix trees can be employed. However, it's also crucial to address edge cases, such as empty strings or arrays with identical entries, and explain your approach's trade-offs. Brute force is straightforward but inefficient, whereas optimized methods may be faster but involve greater complexity. Finally, connecting this problem to real-world applications, like search engines or text processing, can showcase your broader understanding. This problem is closely related to several others on LeetCode that build on similar concepts. For instance, problem 28, which involves finding the index of the first occurrence of a substring, is foundational for understanding substring detection. Problem 139, word break, introduces substring decomposition using dynamic programming techniques, while problem 140 extends this to generate all possible substrings, requiring a more exhaustive approach. Lastly, problem 1062, which focuses on finding the longest repeating substring, involves advanced techniques like suffix arrays or trees. Exploring these related problems can deepen your comprehension of substring operations and help you refine your problem-solving strategies. There are multiple approaches to solving this problem, each with its own trade-offs. The brute force method involves comparing each string with every other string to check for substrings. While simple to implement, its O, in superscript 2 *k, time complexity makes it impractical for larger inputs. An alternative is the sorting-based optimization, where strings are sorted by length, allowing you to limit comparisons to shorter strings against longer ones. This reduces unnecessary checks and balances a complexity of O, n log n plus n superscript 2 *k. For more sophisticated cases, suffix trees or tries offer an efficient solution, reducing the complexity to O, n *k. These structures allow fast substring queries but at the cost of higher implementation complexity and greater memory usage. Each approach has its merits and drawbacks, so the choice depends on the specific constraints of the problem. Finally, set-based deduplication is a simple yet powerful technique to ensure clean results. By storing substrings in a set during comparisons, you can automatically eliminate duplicates without requiring additional checks. This guarantees unique outputs but adds extra space complexity, as the set occupies additional memory. While this trade-off is often minimal for smaller datasets, it's something to consider for memory-constrained environments. Using a set is a practical and efficient way to handle deduplication while maintaining the integrity of your results. Great job! To recap, we tackled a string matching problem and discussed efficient approaches to solve it. Remember the importance of edge case handling and optimizing for performance. Keep practicing, and see you in the next coding walkthrough. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!